Well, in this very special moment, I am overwhelmed with gratitude. Gratitude for my parents, for my family, my friends, my collaborators, for the Royal Swedish Academy of Science and the Nobel Foundation. This can be well understood. But I want to address a special thanks to those two persons. Eduard Kellenberg was my, what is called, Doktorvater. He brought me into science. He taught me to be a scientist. And he explained to me that science is something that should happen in a society. Sir John Kendrew was the first general director of EMBL, and he gave me this tremendous chance to work on this quite strange project of dealing with water in the electron microscope. So why cryo-EM? Because, as you said, we are bags of water. And bags of water made of billions of cells, which are each one bags of water. And if you remove the water, everything floating in the cell or in the body will condensate, will aggregate, and if you are good in arranging the specimen when removing the water, you will get fine aggregates. If you are not so good, you get coarse aggregates, but aggregates you get because fish doesn't fly. So even a very tough object like this T4 bacteriophage, when you dry them on a supporting film, they are in a very bad shape. So people develop remarkable method to preserve the specimen, though the water is removed. One fine method is to dry the specimen in a solution of heavy salt. And the more the water goes, the more the salt concentrates. At the end, you have only the particle with salt around it, heavy metal salt, which hold the structure more or less correctly. Another possibility is freeze drying. You freeze the specimen, and instead of removing the water from the liquid, you remove it from the solid. And it has great advantage, but if you look carefully, the head of this poor bacteriophage doesn't look very healthy. So at that time, my hero is still my hero, is Nigel Hanwen. And we were working in very parallel direction, each one trying all kind of tricks to have a better preservation of the specimen. He had a funny idea. He thought instead of drying the specimen in heavy metal salt is not healthy, he dried them in sugar, because sugar is much better for the material. And he joined his force, as you know, with this guy, with Jacques, and together they got this remarkable result, 1975, voila, marking history. Another person was very important. I moved too much, huh? I'll keep my glasses on. Yes, you have already heard all that. Bob Glaser, perhaps you should stay here. Bob Glaser, during my PhD and so, I did a lot of work just following his steps, but the most impressive message I got from him was this photograph. And these are bacteria quite broken with all kind of substructure of the bacteria. But what is special, we were working with this kind of thing with all our trick for trying to better preserve the specimen in sugar or in any other thing. But here, he had it in ice. In frozen ice, we see the marks of the ice, but it's beautifully preserved. And having seen that, I thought, oh, this is better than anything I've seen before, and this is the future. So 2 years later, I was invited to be group leader at EMBL by John Kendrew with this project, how to deal with water in cryo-electron microscopy. So there is a problem, though. Frozen water is ice, and ice is not liquid water. And it's as bad for a biological specimen to be in ice than to be without water. But we were trying all kinds of tricks. This is our high technology device, and it goes like that. We were trying many, many things, but this is one of the things. We had a nebulizer coming from the right here, high pressure nebulizer, throwing a stream of micro droplets of water or of any kind of suspension, and going through the small slit. Here, the slit. And here, you have a tweezer. And at the top of the tweezer, you have one of these supporting film, this grid that you use as specimen holder in the electron microscope. And while the stream of droplets is going, you let this fall down, in the liquid nitrogen. And we got like that, things like that, a nice droplet of ice. And this is characteristic ice. Now, Alistair McDowell, I can't see him, but he is here, thought, I will do better. And he put here, just in the liquid nitrogen here, a very small beaker where he condensed liquid ethane. And instead of letting the specimen fall down in liquid nitrogen, he let it fall down in liquid ethane. And so he went to the microscope, looked at the object in the electron microscope, and called me, hey, there is something here. And this is what we see. And this is vitreous. This is not crystallized. So we didn't know what this was. The first idea is it's liquid ethane. It's ethane which has been condensed here. No, it can't be. The temperature, at that temperature, ethane should have been gone, should have evaporated. So we thought, okay, we will let it evaporate and we will see what it is. So we turned off the cooling of the specimen holder and we let it warm. I do not remember how long it lasted. Quarter of an hour, warm slowly. And when we came at minus 135, suddenly, but literally in 1 second, the drop transformed into a multi-crystal that we recognized immediately. This was cubic ice. Cubic ice is a different form of ice, quite conventional. We had it studied before in detail in our previous experiment, and electron diffraction confirmed it. It's ice. So if you have a vitreous droplet which turned into ice, you know that you had vitreous water. So what do you do with that? This is Alistair McDowell, vitrification man, great. This was the first Alistair, remember, I said at that moment, oh, we have something great, truly. And the trouble with vitrification, with vitreous water, is that vitrification should be impossible. What does this mean? Yes, I will not go into the detail. I will just mention the founder of cryobiology, Father Basil Louillet, who is a Catholic priest in a very severe Catholic congregation, and he worked for 40 years in trying to produce suspended life. This means immobilizing life in order to obtain typically for breeding, typically. And he makes a lot of money with this, not for him, but for his congregation. And he was working with very good people, and those people with him demonstrate that vitrification was impossible at the end for thermodynamical and complicated reasons that I am not going to explain in detail. So I want to speak about this man for another reason. He was born in Savièse in Valais, Switzerland, and I start school just very close to him in a place which would be here in a small village just on the other side of the valley here. And at present, we have still a nice chalet here, a nice mountain hut here. And for those who love mountains, this is the so-called, this is La Dent Blanche, beautiful mountain. Okay, so having our vitrification, we send it for publication, and we got rapidly this answer: no, it was rejected, you can't bend nature. And they were wrong. They were wrong for two reasons. The first one is that while they were rejecting our paper, they had in press the paper by Bruggeler and Meyer, who was proving that obtaining complete vitrification in pure liquid water and dilute aqueous solution. That means they made the discovery of that vitrification is possible. And then they were doubly wrong, because vitrification is very easy. And with our method, it was reproducible, rapid, and no problem. So what do you do with that? First conclusion: vitreous water is not simple. It's not just liquid water immobilized in the same shape. No, it's something else. But it doesn't matter. It works so well for cryo-electron microscopy that we don't dare to go into the detail. Though, when we will go into the detail, we will certainly understand very important things about water that we yet don't know. And perhaps it will be important for biology also. The second ha-ha can be explained like that. We work with these grids, and on the grids we have a thin film, and we spread the specimen, the solution on the grid. But this is difficult because water has high surface tension, and what water is to form a sphere, minimize the surface, and trying to maximize the surface on a grid is just technically difficult. You have to arrange the surface so that two high numbers just come equal and negate one and the other. It's a complicated process. And my collaborator, Marc Ardrian, at that time, he died, unfortunately, very badly very stupidly after his retirement. And this is a very remarkable person. He is very stubborn, extraordinarily cultivated, and he has an enormous culture, and very stubborn, and he was not at all interested in spreading the water on the grid. So he wanted to have no support. And he was working, trying to get the specimen on the holes of the grid without support. I was quite opposed to that, because there is no chance. But because I knew the physics, but he got that. And it turns out that it was not so, it was quite easy, very easy, in fact. And this is a typical example. On a hole of the grid, which is 20 micrometer broad, you get this a tenth of micrometer thick layer spreading over the whole grid. So the film is 200 times thinner than broad. Technically, in terms of energy, it's quite strange, but it works well. Later, we understood why there are interesting energy and thermodynamic reasons which explain all that, but at that time we were not aware of that. So the method, and now comes the most difficult part of the seminar. Voila, hop. This is how it should go. So you have a grid on a tweezer. You have a beaker with liquid nitrogen. You have liquid ethane, and tac, hop, c'est loupé. We try again. Voila. Before you came with the blotting paper, as you explained, in 1 second the grid, the liquid disappear in the, oh lord, yes, the water disappear goes in the blotting paper, but the last tenth of a micron takes another second to go away, and you have time to let the grid fall down and the sample get vitrified. This was 1984. This was rapidly published. The general director of EMBL was a new person, and he was not Leonard Philipson, and he was not very happy with those physicists working with water. But so we worked with his pet virus, the adenovirus, and when he got this nice photograph, he was convinced, and we became the best friend in the world. And so was it. And you notice, but of course, you have heard more, and you will hear much more from Joachim in a moment, when you have the particle floating in water, with all orientation, you can make 3D reconstruction. And so we had this, 1986, this model of a virus at 35 angstrom resolution. 35 angstrom resolution. And so came the beautiful word blobology. Blobology. Yes, this is blobology. And then a lot of people continue to work, were working before. We were also working, but those you understand are they more important than the other? I guess yes, but there were plenty of other. And so we had 30 years. We had 10 times better resolution. 10 times better resolution, this means 1,000 times smaller volume. This means 1,000 times more density of information. And this is not a small achievement. And 3.5, 35 to 3.5, both. These are just numbers, but 3.5 mean seeing atoms. And when you see atoms, then you are a chemist. And therefore, you have, from cryo-EM, all the power of chemistry, which means that you see how filaments aggregate together, how the brain becomes senile, perhaps, because of that. You say, perhaps you will see how you will find a drug which will prevent them to aggregate. Perhaps, now I come to the end and to my reading. Now, perhaps we will understand how to do medicine with that. There are plenty of people who are interested with results there. And science will continue. It will take time to explore the brain. We may understand how we think perhaps conscience will emerge. This is knowledge without limit. Oops. Voilà. Yes, but knowledge has its consequence. Knowledge makes what our lives are. When the year we discovered we published the thin film vitrification method, I got my first personal computer. Now 1 billion of people is sitting in front of a computer screen for most part of their day, and communication between people is fundamentally changed. The father of my grandfather was living in scarcity. He was never sure to be able to bring home the minimal required for a decent life for his family. We are now submerged with excess, and the world climate is getting rugged. And the glacier just above our mountain hut is collapsing. We have a problem. Science sans conscience n'est que ruine de l'âme. This is not very new. Rabelais, 500 years ago. But now it's getting very actual and very urgent. Well, yes, and, oh, sorry. Very urgent. What can we do? It's very urgent. What can we do? One thing is certain. We scientists must come out of our ivory tower and be involved in the society for which we produce knowledge. That knowledge can have equally good or bad consequence, and we must become more aware and responsible for these. This is the reason why, more than 20 years ago, we introduced in our university a compulsory curriculum, biology and society, because we want our students to be as good citizens as they are good biologists. This is good, but this is not enough. How can we be as good in using our knowledge for the well-being of all as we are in producing it? I don't know. You see, we are used to speak freely, but this part is in some ways too important to be said like that. Therefore, I want to write it, wrote it down, and it's make it very complicated. Yes, I don't know, but we must fight for our most precious good. Namely, we must protect and fight for for knowledge. Knowledge is our common good. And which must make out of it the best for the well-being of all, now and for future generation. Imagine if, it's easy if you try. Imagine, for example, we think about health. Imagine that we take the WHO, the World Health Organization, an organism of the and imagine we give to this organism all the knowledge about health and about medicine, about how to help people health. And we give this organism the right and the power to do the best with this common knowledge. Of course, we will give those who produce the knowledge the right reward for the effort. It would not be hard to do. Imagine. You may say I'm a dreamer, but I'm not the only one. I hope someday you'll join us, and the world will live as one. Thank you.